Okay, AP Chemistry class. This is your lesson for empirical formula. I wasn't able to, I intentionally didn't put it on line last night, but we worked on it in class. Unfortunately today, Tuesday, I had to go to a meeting and wasn't able to be in my classroom, but hopefully this will help you if you've having some challenges with this. And it's fairly long, so I'm going to get going on this. So empirical formula. What is an empirical formula here? Well, let's go ahead and do these first. Here's some examples. What it really is the molecular formula, which is the actual formula of a molecule that exists in nature, as it actually exists in nature. So it's the molecular formula reduced to a ratio of, reduced to the lowest ratio, just like reducing a fraction of its atoms. Let's say it's constituent or component atoms, but we need to go there with the language of its, I was about to write it, of its atoms. Okay, what's it used for? So what do we use this thing for? Empirical formula is an intermediate step in finding the actual molecular formula, the actual formula for a specific molecule. And it's an intermediate step, means it comes in the middle of the process of figuring it out. And what happens is you get some actual experimental results in a lab, such as getting the grams of the products of a reaction, and using that you can figure out what the empirical formula of the compound was that you started with. Okay, so that's what it is. And you know, that definition will make more sense when you see some examples, okay? All right, so let's reduce all these to their lowest number ratio of atoms. H2O, that's a 2-to-1. You can't reduce that any further. There. Here, these are all even numbers, so you can see that they can be divided by 2. So this one would be, or they can actually all be divided by 6, right? So 6 goes into this once, twice, once. So it's C, H2O. Okay, and that's the lowest ratio of atoms. That's the lowest ratio of atoms that you can get. There's 2 hydrogens for every carbon and 2 hydrogens for every oxygen. Okay, how about this one? It's also even numbers. You can divide this by 2. CH4 is already in its lowest terms. This one's divisible by 2. Hydrogen peroxide is a 1-to-1 relationship. 1 hydrogen for every oxygen, so that's HO. Again, divisible by 2. Divisible by 2. And also divisible by 2. Okay, so simple enough. That's how you get the empirical formulas given the molecular formula. Now we're going to do some simulations of being given data from a lab and figure out how to find the empirical formulas for a few compounds. So you know you started off, you know certain things. You know you started off with some sort of an HO compound, but you don't know how many H's and you don't know how many O's. So that's what we're trying to find out here. So a decomposition reaction would be HO with some subscripts there would produce a certain amount of H and a certain amount of O. You're breaking it apart. That's called a decomposition reaction. Okay, so we're saying that it produces 0.857 grams of hydrogen and 6.86 grams of oxygen. What's the empirical formula for this compound? So always in chemistry, we got to get things, anytime we're dealing with a chemical formula or chemical compound, everything, whether it's the coefficients or the subscripts here, are in moles. So you have to convert to moles. Grams don't do us any good. So let's go ahead and do that. First of all, let's find out the molar mass of hydrogen. So 1 mole, and we're talking hydrogen atoms, not the molecule H2. And that's going to be 1.01. You get this right off your periodic table. 1.01 grams of H. And 1 mole of oxygen, right off your periodic table. Just a single oxygen atom. And that's going to be 16 grams of O. Okay. And remember, so now remember you can make ratios out of this. 1 mole of hydrogen over 1.01 grams of hydrogen, or the other way around, 1.01 grams of hydrogen over 1 mole of hydrogen, and you can make the same 2 types of ratios for oxygen. So we're going to start with 0.857 grams of hydrogen. We need grams of hydrogen on the bottom to cancel from our molar mass ratio, so 1 mole hydrogen over 1.01 grams of hydrogen equals, and I should have my calculator ready here. Alright, so it's 0.857 divided by 1.01. Okay, and that's going to give us 0.8. Again, I'm being really loose with the, not real precise here with the digits, sig figs and all. But it's going to be 0.85. Let's go with that. 0.85 moles of hydrogen. Okay, go ahead and do the same thing with oxygen. Oops. Okay. Mistake I make all the time, be careful. Not the molar mass, 16. Grams cancel with grams. Put them there too. And we get 0.43. Okay, so I haven't gone over the law. It was developed by a scientist a couple hundred years ago named John Dalton, who came up with this idea that atoms in a molecule have to combine in whole number ratios. You can't have fractions of an atom. And this is before they really even knew what an atom was. They didn't even know anything, what a proton was or a neutron or an electron. They just knew there were these things called atoms. And we're going to go over Dalton's laws. It's kind of we kind of neglected that because it wasn't really critical, but we're going to go over those here in a very short time this week and just review what Dalton's laws are. There's 4 of them, and we'll talk about those. Okay, so I have these numbers of moles. So in other words, this is some number of hydrogen molecules, some big batch of hydrogen hydrogen atoms, and some big batch of oxygen atoms. So they got to combine in whole number ratios. So we're looking for some whole numbers relationship between these two. So you take the 2 and you create a ratio. And I think I'm going to change the text where I said you have to put it over a 1. What you're really doing is you're putting it over 0.43, and that one is for hydrogen. And for oxygen, it's going to be, you put the smallest one in the denominator, so 0.43 is smaller than 0.85. So the smallest one is always going to be 1 because it's always going to have its own number in both the numerator and the denominator. You're dividing everything by the smallest number of moles. Okay, so this is obviously going to equal 1. And you look at this, 0.85 divided by 0.43. And that gives you 1.98. Pretty close to 2. Is that close enough? Yes. If it's 1.8 or something, or 1.7, then no, that's not close enough to round it. But this is within 2 100ths. And so yes, this is going to be a 2 to 1 ratio. Okay? So this is 1 to 1, 2 to 1. So there's 2 of these and 1 of these. All right, now since those are already whole numbers, we don't need to do our little trick of multiplying everything by a whole number until we get whole numbers. We already have whole numbers. So we're going to go ahead and write our formula. It's H2, this number right here, O1, but you don't write the 1, so it's H2O. So that's our chemical formula, okay? Again, this process of dividing by 1, I think I'm going to reword that. It's what I got out of a book, but, you know, I think it's clear enough what's going on here. All right, so that's the empirical formula is water, and since we know water is actually the molecular formula for water, H2O, then we've got the molecular formula, but you don't always know that. This could have been something that's H4O2, it could have been H6O3, anything that's a 2 to 1 relationship between hydrogen and oxygen. All right, let's keep going. And this was the step I said we didn't have to do in this problem because we already had whole numbers. Okay, and I already did this, but I'll do it again just to make the question, just to fulfill the question. Okay, here we go. Okay, now we have something with nitrogen and oxygen. We're going to do the same thing. Again, always stop the video and see if you can do it on your own. But I've laid out the steps here. It's really teaching you as you do the problem step by step. So see if you can do this one. Okay, and if you stopped it, we're back. So here we go. So nitrogen is 24.5 grams of nitrogen. And our molar masses, let's just write that out over here, 1 mole of nitrogen. And that's 1 atom, not the diatomic molecule, is going to be 14.01 grams of nitrogen. And oxygen we've already done. Okay, so we're going to do this multiplication here. Put the moles on top. Grams nitrogen, grams nitrogen. And we get 1.75. And that's moles of nitrogen. Remember, in a chemical equation, what's going on is each atom or molecule is matching up with other atoms and molecules. So we're interested in numbers of atoms and molecules in terms of moles, not grams. That doesn't help us. Okay, I didn't leave myself a lot of space here. My bad. Should have started that somewhere else. So let's go ahead and do oxygen. And we have 70 grams of oxygen, so I'm going to do that one up here. And I should have written grams of oxygen here. So grams of oxygen cancels there. So we got 70 divided by 16. And that gives us, ooh, that's a weird number, isn't it? Okay, but it is what it is. 70 divided by 16 is 4.375. I recognize that number, though, as a fraction. Maybe you do. 0.375 is 3/8 as a fraction. So eventually we're going to get a whole number here, but it's not going to be pretty. Okay, this one's going to be a little dicey. Okay, so the smaller of the two numbers, 1.75 or 4.375, well, actually, you know, it might be neater once we do the division. So let's see how it works out. So 4.375, so this is for oxygen, 4.375 over 1.75. And don't worry about units of measure. They're going to cancel out. We're just getting a ratio here. And then for nitrogen, it's going to be 1.75. The smaller number always goes on the bottom. So one of them is always going to have its number of moles over itself. That always works out that way. That's a 1. And what's 4.375 divided by 1.75? 2.5. Oh, isn't that a nice number to have? So yeah, you really didn't have to worry about this. It was that one that we're getting to. Okay, so what does that mean we have? Here's our formula. It's N1O2.5. But we can't have decimals or fractions in the subscript of a chemical compound. So what we're going to do is multiply 1 and 2.5 by each whole number until we find that both of them turn into whole numbers. So 1 times 2, let's start off with 2. We're just going to start off and then go 3, and then go 4, and then go 5 if we need to. So 1 times 2 equals 2, and 2.5 times 2 equals 5. Well, that didn't take long. We have 2 whole numbers here. So now we can properly write our empirical formula. And actually, I should have done that down here. Okay, it doesn't really matter. I mean, as long as you're working the problem, these are just to give you instructions here. Okay, but we got 2 and a 5. So that means our subscript, the 2 belongs to nitrogen, so it's N2O5. That's our empirical formula. Okay, again, we don't know that that's the molecular formula. The molecular formula could be N4O10, could be N6O15. There's an infinite number of possibilities, but it is out there somewhere, and we're going to talk about how to find that very shortly. Not today, but later on. Okay, let's go. All right, now we got one with 3 elements in it. Okay, and this is the one I did on the board today, so I hope you got that one down then, but let's go ahead and do it in case you didn't. So molar masses up here. I hope in the midst of all the stress of school that you kind of learn to enjoy these problems. They're kind of puzzles. A lot of chemistry problems are little puzzles, and you know, with all the stress of all the other classes you got and getting through all this material, I hope that you'll kind of learn to enjoy them. When I started to decide I want to get good at science and try to at least become as good as I could become, it was a game to me, and I wanted to solve problems, and I never wanted to let the problem beat me. That's kind of the way I looked at it. I'm going to beat this problem. I'm not going to let it get the best of me. Okay, so there we go. There's our molar masses. So now we go ahead and take the grams, and we have to convert the moles. Chemistry speaks to us in moles. So this is the one I stumbled on today. So it's 60 grams of carbon times 1 mole. And again, don't ever get too tired or lazy to write units of measure and compound. It will save you so many headaches. There's a temptation is to shortcut it and just scratch down the number and move on. Don't do that. You get in so much trouble in these problems if you do that. Okay, grams of C. Divide 60 by 12.01. And boom. 4.99, we're going to call that 5. That's good enough for me. 5 is good enough right there. Next, we have 4.48 grams of hydrogen times 1.01, messed that up. 1 mole. 1 mole of hydrogen over for every 1.01 grams of hydrogen. And what's that give us? That looks like it's going to give us something close to 4.5, right? Maybe. Whoops. At 4.44. That's what we got in class today. Moles of H. Okay, and I'll squeeze the oxygen over here. It's 35.52. So 35 divided by 16. And it's 2.22. So these are my 3 this is how many moles of each of these I have. So I'm trying to find ratios of moles and how they relate to each other, and then turn them into whole numbers. So 2.225, 4.44. So the smallest of those three numbers is 2.22. So let's start with carbon. It's 5 over 2.22. It's carbon. H is our next one, and H is 4.44 over 2.22. And finally, O is 2.22. Always the smallest one is always going to be 1 over 2.22. So this one's 1. This one's obviously 2. And we'll circle those. Okay, and then 5 divided by 2.22. And that gives us 2.25. I'm going to write that here. There. Okay, 2.25, 2, and 1. So that means our formula would be C 2.25 H 2 O 1. But we can't have a decimal there in the subscript. So what we're going to do is take these numbers. I'll start way over here. And take 2.25 times 2. And I can really stop right there, but I'm going to do the whole thing here. And I'll tell you why I could stop right there. And this is 2 times 2. And the last one is 1 times 2. I'm taking each of these numbers right there and multiplying them all by 2. I'm trying to get them, all three of them, to be a whole number. So 2.25 times 2 is 4.5. That's why I'm saying you could have stopped right there. As soon as you see that's not a whole number, you don't need to do the other two, but I'll go ahead and do them anyway. There's 4, and 2 times 1 is 2. Okay, that didn't work. Now we're going to try 3. 2.25 times 3. 2 times 3. 1 times 3. Again, this one's going to be 6.75. You don't need to go any further because that's not a whole number. So now we just got to keep incrementing it up, okay? 2.25 times 4, 2 times 4, and 1 times 4. So 2.25 times 4, do that on your calculator, you get 9. That is a whole number. That's what we were looking for. 2 times 4 is 8. 1 times 4 is 4. So there are the subscripts for our empirical formula in order. So it's C9, H8, O4. Okay, and that's your final answer for your empirical formula for this compound. All right, let's push on. Now we're going to get one where we're actually dealing with a chemical reaction. And I ask you, what type of reaction is this? We're going to cover reactions this week. Just learn the names of the different types. There's really only 5 types. There might be a 6th, but depending on what book you read. But there's really 5 types, and this is called a combustion reaction. It's always a hydrocarbon or a carbohydrate of some sort. So it's either a CH or a CHO. And we're going to do some with CHOs. They're a little more complicated. But let's start off with this. It's good to know how to do a CH compound. So it's always a hydrocarbon burning. You light a match to this in oxygen. And if it's methane, for example, that's what the burners in our room put out. You burn it in an oxygen environment like air, and you're going to always get out carbon dioxide and water. The only thing that changes is, depending on what the hydrocarbon is, will depend on how this equation balances. So you don't need to balance it. You can't, because you don't know the subscripts here. What the object is to find out what these question marks are for subscripts. So this is called a combustion reaction. And you're trying to identify the empirical formula of this hydrocarbon, okay? So let's go ahead and turn the page and do that. All right, so there you go. You're given grams just like you were in the previous one. And I'm going to go ahead and write the reaction over here again. It's C question mark, H question mark, and that's not to imply that the two question marks are the same. We call it CXHY. I mean, it could be two totally different numbers with different variables. Okay, plus O2, and that's going to give you carbon dioxide and water. Okay, so this one requires a little bit of thought in that you got to say, okay, we're given 5.72 grams of CO2. It's not telling us just carbon or just hydrogen. It's telling us of this entire compound and of this entire compound is how much we're given. So what you have to reason is this. Well, first of all, let's just draw, if you want to still use your box, remember you have moles up here, you have molar mass in the middle, no gases involved here. If you still like to do this, do it, and grams on the bottom. That's our world. We got to translate grams into moles. So grams of CO2. So we have 5.72 here, and for the H2O we have 1.17. And I'm going to go ahead and assume you're going to know how to do the molar mass, or maybe I shouldn't. It's C is 12.01 times 1. I don't want to assume anything at this point. Some of you are there, some of you aren't. O, and there's 16, and you have 2 oxygens in CO2. So this is going to be 12.01. 16 times 2 is 32. When you add those two for carbon dioxide, if you don't have this one memorized, you will very soon, 44.01 grams per mole. Okay, all right. So that's our molar mass. So we can put that right here, 44.01 grams equals 1 mole. And that's for CO2. It's in that column, so I'm not going to put the CO2 on the end. Okay, here we go. Water, same thing, is write it up here. You got 2 H's. And you got 1 O. And that's going to give you 2.02. And this one's going to give you 16. You add those together, and you get 18.02 grams for every mole of water. So 18.02 grams equals 1 mole. Okay, all right, so let's set up our equation first for carbon dioxide. Remember though, we don't want to know how many moles of carbon dioxide, we want to know how many moles of carbon. That's going to require that we do a step that we haven't done in any of our previous assignments. So let's get started. We have 5.72, those are grams, 5.72 grams CO2. Now we're going to convert molar mass CO2 to get it into moles. So it's 1 mole CO2 for every 44.01 grams of CO2. So now what we've gotten is we've gotten moles of CO2 with this so far. But now we're not interested in moles of CO2. We're trying to figure out how much carbon. So what you'll notice is there's 1 atom of carbon for every molecule of CO2, or we live in the world of moles now. There's 1 mole of carbon for every 1 mole of CO2. There's a subscript 1 right there, that's moles, and there's a subscript 1 right there that we didn't write, that's moles. So it's a 1-to-1 relationship. So that means you're going to convert, you want to end up with moles on the top as your last man standing, so moles of carbon on the top and 1 mole of CO2 on the bottom there. So moles of CO2, grams of CO2, grams of CO2. There we go. And so over here we end up with basically a lot of 1s there, but it's 5.72. Divided by 44.01. And that's going to give us 0.13. Okay, so 0.13 moles of carbon. So what that means is if we ended up, the only place that this carbon could have come from is here. So you don't create or destroy carbon, either grams or moles, doesn't matter which you're talking about, it stays the same. It doesn't disappear, it doesn't go away. So if we have 0.13 moles of carbon here, we have 0.13 moles of carbon here. If you want, you can write that right here. Okay, or you could have written it anywhere down there too. That's how many moles of carbon we have. Let's do the same thing for hydrogen. All of the hydrogen that came from this hydrocarbon had to end up in the water here. There's no other hydrogen over on this side. So it all had to go there. So however many grams or moles, whichever you want to talk about, we have here, we have to end up with that many grams or moles of hydrogen atoms there. Okay? So let's go ahead and figure that one out. So we have 1.17 grams H2O. So now we're going to convert to moles of H2O first. For every 18.02 grams per mole. And that means 6 times 10 to the 23rd water molecules in a glass of water is going to weigh or have a mass of 18.02 grams. Okay, this one's just got one additional step that's a little... We're interested in hydrogen atoms. This is not an H2 molecule. It's 2 hydrogen atoms. It's 2 moles of hydrogen. So it requires 2 moles of hydrogen to make 1 mole of water. So we need to, since we're interested in how many hydrogen moles we have, not how many water moles we have, we're going to do that one further conversion. So there's 2 moles of hydrogen for every 1 mole of H2O. So moles H2O cancels there and there, grams H2O cancels there and there. This is what we have left. So that's going to equal 1.17 times 1 times 2 divided by 18.02, and boom, it gives us, hey, pretty much exactly the same numbers, 0.13 mole of H. Okay, so that kind of makes our life kind of simple here. It means neither one of these are both exactly the same size, right? The number of moles here, number of moles here. So, in fact, I could write it up here just like I did for carbon. So it doesn't matter which one you put on top. It's going to equal 1. Okay, so it's a 1-to-1 relationship. We have exactly as many moles of carbon as hydrogen as we have of carbon. Doesn't matter which way you write it. So our empirical formula is simply going to be CH. It's a 1-to-1 relationship. Okay, and that's your empirical formula for this compound. Now let's try this. Let's say these were our measured values in the laboratory. We did the same combustion, and we ended up with 10.6 grams. And there's ways that you can trap the carbon dioxides. The chemists know how to do that in laboratory. And you trap the number of grams and count the number of grams of H2O that you got. You weigh it, you put it on the mass, and then we can figure out what the empirical formula of the hydrocarbon, the CH compound that we use to get this. So let's go ahead and do that. We're going to exactly set this up the same way. So we'll start with the carbon again. So 10.6 grams of CO2. Okay, there we go. Good. Okay, so now we're up to grams of CO2. We have that same 1-to-1 relationship. Nothing's really changed from the previous problem except the number of grams. So it's a 1-to-1 relationship. So 1 mole of carbon for every 1 mole of CO2. And our answer is going to be 10.6 divided by the molar mass of carbon. And that's 0.24, 0.24 moles of carbon. Okay, so for this problem, I can write that right here. I'll put it on the bottom here. That's how many moles of carbon we have for this problem down here. Same thing with hydrogen, 4.88 or 4 grams. Yeah, same thing for hydrogen. which we have to get by using the water. So grams of H2O. Okay, grams H2O, and now we've got to convert the same thing. We have 2 moles of hydrogen atoms for every 1 mole of water molecules. So we're going to have 2 mole okay, and now we do the math. 4.88 times 1 times 2 divided by 1 divided by 18.02, and that gives us 0.54. So you see we didn't end up with the same numbers like we did above. The problem above was a little bit easier. Okay, so now what do we do? Think about it. What do you do? That's moles of H. What's your next step? Go back to your previous problems review. So yes, you set up the ratio with the smaller of the 2 amounts of moles. That's this one on the bottom. So for oxygen, we have 0.24 over 0.24. That's the smaller one. For excuse me, I said for oxygen, for carbon. Sorry about that. For carbon, yeah. And for hydrogen, we have this number. 0.54 over 0.24. Again, we don't have to put units because they're all going to cancel out. Okay, and what does that give us? That's going to give us an interesting number. It's not going to be a whole number. And it's 2.25. Saw that number before in a previous problem, right? Okay, so there you go. So this one equals 1. For carbon, and for hydrogen it's 2.25. So the way we could write this is C1H2.25, but of course we know we can't leave that decimal number there. So let's just start multiplying through. We've already done this once with the 2.25, but let's do it again. So you have 1 and 2.25. We need to get them both to be whole numbers. So we're simply going to multiply first by 2. And that equals 2. We're going to multiply this one by 2, and that gives us 4.5. Not a whole number. Let's go over here. 1 times 3 equals 3, and 2.25 times 3 equals 6.75. Still not a whole number. Let's come over here. 1 times 4 equals 4. And 2.25 times 4 equals 9. That's the same whole number we got in the previous problem. So there's our whole numbers. So it's the hydrogen on the top and the carbon on the bottom. Check that. That's the carbon on the top and the hydrogen on the bottom. We got those backwards. So these are going to be your coefficients. So it's C4H9, and that's your empirical formula for this compound. Okay, now we're going to hit some review problems. Going to always try to throw some review problems at you. You can either go back and watch the videos, or you can watch this. Try to do them. See if you can remember them. If you can't, because it might have been. And we're going to get sometimes where I may give you some from a month before. But see if you can do this. Okay, so I'm giving you an already balanced equation. And let's see. Limiting reactants. So first thing we're going to want to do is convert to moles. All right, we've got grams up here. And so let's go ahead and figure out how many moles that is. So first, the molar mass of Cu2O. So get your periodic table out. Grab mine. Let's get that back. Okay, So let's do this, okay? It's a little bit of practice on this. Cu, you have 2 coppers, and the molar mass of copper is 63.55. And then you have a single oxygen. There's 1 times, we know this one is 16. And 63.55. It's too late in the day. I'm too tired to do it in my head. I really am. 127.1. Okay. All right. So that means what we have is, well, we got to add them first, and that's going to be 143.1. So 1 mole of Cu2O equals 143.1 grams of that. There's our molar mass conversion for that. And the other one is just carbon. So that one becomes easy for us. Okay. And so 1 mole of carbon equals 12.01 grams of carbon. All right. So let's go ahead and figure out, we have this much. So let's figure out each of these. We have 4.68 grams of Cu2O. We've got to convert everything to moles, as we always do in chemistry, times 1 mole over 143.1 grams. Grams cancels, grams cancels. Boom. And now we got to do the math on that one. 4.68 divided by 143.1, and it gives us 0.33. 0.033. Again, I'm being very arbitrary about how many decimal places I go. 0.33 moles of Cu2O. All right. I didn't leave myself a lot of space to do the other one, but that's, let's see, that's pretty, let's see, 58.58 shouldn't take up much space. So 58.87 grams of carbon times 1 mole carbon would be 12.01 grams, molar mass conversion. Carbon, grams cancels, so it's 58.87. 58.87 divided by 12.01. I'm off screen, sorry about that. Okay, 58.87 divided by 12.01, boom. 4.9. Let's see. Okay, so we have 4.9 moles of carbon. We have 0.033 moles of Cu2O. So now we're going to run the reaction twice. This is the way you always do limiting reactant problems. So first we're going to run all of the Cu2O, and then we're going to run a second time, using the same exact amounts, all of the C. All right, so here's our 4 little boxes here. Draw boxes if you want. Don't draw boxes if you don't want. So we were given this many moles of Cu2O. So in the Cu2O column and in the all Cu2, we're going to say, what if we burned all of that? I use the term burned. I shouldn't. It's reacted. What if we reacted all of that? So it's 0.033 there. Down here is all of the carbon. And over here in the carbon column, we're going to say, what if we reacted all of the 4.9 moles of carbon? It looks like this problem is going to be a little lopsided here. I got this out of a book. It's a little bit odd. So these are moles we're talking about. So what's the relationship between this and this? Remember, whenever you don't, I would like you to always get in the habit of writing a coefficient there until you really become adept at chemistry. You don't normally write a 1 for a coefficient, but I want you to see the numerical relationship is 1 to 1. So for every mole of copper oxide, cupric oxide, you're going to need 1 mole of carbon. So for every 0.033 moles, you're going to need 0.033 moles there. It's an easy one to spot. And going back, for every 4.9 moles of this, it's a 1-to-1 relationship. You need 4.9 moles of the Cu2O. All right, so now we go ahead, we circle this because we know we have that much. We circle this because we know we have that much. Again, I just write the word yes, we know we have that. Yes, we know we have this. Now, we're going to ask ourselves, do we have at least 0.033 moles of carbon? Well, heck yeah, we got 4.9 moles of carbon, so we got way more than this. So that's a yes. Now we come over to this box. Do we have at least 4.9 moles of Cu2O? No way, we only have that little tiny amount right there. So our no is right there. So the limiting reactant is this one, Cu2O, because that's the column that our no is in, is the limiting reactant. Okay? The reaction that's going to work is the row. It's a row up here. It's one of these two rows. Some of you were a little confused when we were doing this before. It's either this row or this row. It's this one right here. This is the one with both yeses in it. So I'm going to draw it all the way over there. So if I want to figure out anything here, my boxes are going to be right here. They're not going to be down here. There's nothing down here because this reaction on the bottom doesn't work. Okay, so limiting reactant is the column, the Cu2O, that the no is in. How much excess reactant remains in this reaction? Well, I'm going to just do it in moles. You don't need to convert to grams. It's how much. So the yes reaction is the one on top. So if we're going to run this reaction, the one that works is this one. 0.033 is what we use, but we started off with 4.9. We're going to have a lot left over. 4.9 minus 0.033, and what's that equal? That gives us 4.867 moles. We're still working in moles of carbon is left over, is in excess. And if we want to convert that back to grams, we use the molar mass for carbon, which is 12.01, and that will give us how many grams of carbon that we get to go put back into our little carbon jar to use the next time, because we didn't have to use it. Okay, how many grams of copper can be produced? So it's asking for this down here. Okay, I'm going to draw a box down here where I didn't have one before. So we need to figure out how many moles of copper we have. And then we need to use the molar mass for copper to get outside here. So let's go ahead and figure out what is the molar mass of copper. It's just of a single copper atom. And we have that number over here. So 1 mole, we're just talking just pure copper this time, of Cu equals 63.55 grams of Cu. So that's the molar mass conversion we're going to use. So first, let's figure out how many moles of copper we have. What goes in that box for moles? Well, you notice that these are 1s here. Let's just pick this one. This is a 1. This is a 2. So however many moles we have here, we're going to have twice as many moles here. So you're going to take this number, 0.033, and multiply it by 2. And that one I think you can do in your head. It's 0.066. So that's how many moles of copper we have produced by this reaction on the top. It's the one that actually works, the one where we don't run out of either of these. Okay, now we want to figure out how many grams that is, so we just do a molar mass conversion. 0.066 moles of copper times, now we got to have moles on the bottom here and grams on the top because we want to end up with grams. We're trying to get down here grams of copper. Okay, so that's going to be 63.55 grams of copper and on the bottom is 1 mole, not 2 moles. The 2 was used to do this conversion, the moles to moles. It's not used here. This is a 1 mole for every 63.55. Okay, I keep beating on that because it's a very common mistake. So moles of copper goes away, and now I multiply 0.066 times 63.55. And that gives me 4.19 grams of copper is produced from that reaction. Okay, so there's that answer there. Okay, how many liters of CO2, now CO2 is the only gas we have in this reaction, will be produced at STP, and let's just kind of learn these terms. STP, standard temperature and pressure, or just standard temperature pressure. STP, and it's 0 degrees centigrade, the freezing point of water, but for a gas that's not very cold. The freezing point of carbon dioxide is somewhere around 200 or so. I don't even know, but if you looked it up, Googled it, and that should be CO2, of course, it's way down there. So 0 degrees is nothing compared to minus 200 degrees. So gas is not being frozen. It's still a gas. And 1 atmosphere is just think of it as the pressure, the air pressure in this classroom. We're at sea level, and it's the air pressure at sea level, the typical air pressure at sea level. Okay, so we remember there was a relationship that 1 mole of any gas at STB, okay, any gas, is going to equal to 22.4 liters. All right, so let's go ahead and do that. So it's asking us how many liters of CO2 gas, so liters CO2. And first of all, we got to find out how many moles. So there's a 1 right here. So all you got to do is find some other number to relate it with. Well, there's a 1. So if 1 mole relates to 1 mole, every mole of this is going to produce 1 mole of this. 0.033 moles of this is going to produce 0.033 moles of that. So that's what we're going to start with over here. And I'm not going to draw the liters up here. It was somewhere up on the top when we did this before. So 0.033 moles CO2 times 1 liter, give me 22.4 liters. Of anything. That's not why I'm not right. Well, let's go ahead and write it. We said we were going to do that. For every liters of CO2 for every 1 mole of CO2. Moles cancels, moles CO2 cancels. So now we have 0.033 times 22.4. So we're going to do that. And that's going to be 0.033 times 22.4 equals, and that's going to be, I'm going to write it down here, 0.74 liters of CO2 gas will be produced. And there's your answer for this one up here. Okay? All right, let's finish up with something we touched on very quickly. So isotope notation. So isotope notation is used because especially when you're dealing with isotopes. If you're not dealing with isotopes, it's not the subject of what you're studying. You don't really have to deal with it. But the way it works is you take the atomic symbol, in this case Li, and down on the bottom you put the atomic number. So lithium has 3 protons. There's the atomic number. So it's 3. So let's say it has 5 neutrons. Your typical lithium atom, if you round 6.94 up to 7, and you subtract the 3 protons from that, your typical lithium has 4 neutrons. But we're saying, what if it has 5? So what you're simply doing is taking the number of protons plus that number of neutrons that you're saying. It's an isotope, so it has a different number of neutrons than the typical lithium atom. So 3 plus 5 is 8. So you put the mass number It's always a whole number. It's not a decimal number because we're not taking an average. This is the actual mass of this particular isotope of lithium. So it's not a decimal number. It's exactly 3 protons plus exactly 5 neutrons. Gives you exactly 8 for the mass number. And that's how you write it. Li. And like that. Okay. Now that you know that and remember that, do the next 2 on your own. Okay, I'm back. Phosphorus is going to be P. And it has 15 protons, atomic number of 15. And you're saying it has 18 neutrons. So again, we're not dealing with any decimal numbers. It's 15 plus 18 is going to be 33. So the mass number for this particular isotope is going to be 33. Your typical phosphorus is going to have 16 neutrons. So this number for your typical phosphorus, the one that there's the greatest number of, remember we did the mass spectrometry and we figured that out with those ratios and that how many of each there was. That would be a 31 for your typical phosphorus. Okay, next is carbon with 8 neutrons. We put a C. We look at our periodic table. We see that carbon has 6 protons, atomic number, so it's 6. And 8 neutrons is 8 plus 6 is 14. This is the very famous isotope of carbon that's used to date fossils and lots of old stuff. We'll talk about how that works. We don't have a lot of time to talk about that, but it's kind of an interesting little side topic. So that's how you write the isotope notation for carbon-14. By the way you can also write these if you had to is C-14, P-33. We haven't talked about this before. And Li-8. Okay, that's also the way you could write that. Okay, that takes care of it. We kept it under an hour. You got all the answers. Let's have this done when you come in tomorrow. We're going to continue to work on the POGO. We're going to get into nomenclature, and then we'll hopefully have a good time. We might even have some goodies for you when you come. I don't promise, but I'm going to see what I can do. Okay, have a good evening.